we know that there's a whole class devoted to differential equations. So obviously there is more than one type of differential equation, otherwise we wouldn't have an entire class. So in calculus, the differential equations that we're going to solve are going to be our very basic type of differential equations. Kind of like when you first learned pre-algebra, before you got to algebra, all you really focused on were these very simple linear equations, like 2x plus 5 equals 7, and things like that. So the type of equation we're going to talk about today is like your basic type of differential equation. Remember, we're only going to focus on first order, and as a reminder, first order means only dy dx, first derivative. Today, we will add in some second order differential equations a little bit later, but that's all we're going to focus on today. And then tomorrow we're going to put in some word problems to go with it. Some real world examples that go with these simple types of differential equations. So the process or the technique that we're going to work on today is called separable or separation of variables. Separable differential equations. So, two types of equations that we're going to come up with, just like we dealt with our slope fields. We know in our slope fields, we were able to look at what the family of functions should look like as the solution, and then we could come up with what we call a particular solution, one curve through there, if we knew an initial condition. Same idea here. We're now going to learn how to solve the differential equation, and we will either get a general solution, or if we have an initial condition, we'll get what we call a particular solution. Okay? That's what we're going to work on. So kind of like the slope fields, we'll have two types, a more general one and a more specific one. Okay? Now, separable differential equations, the idea behind it is straightforward enough. Sometimes the math that goes with it is where we got to bring back some of our integration skills, which will be good. So, first order differential equation that can be solved using separation of variables is one where we can write it with, get this, the variables separated across an equal sign. I know, this is shattering, right? So our goal is to get it so that we separate those variables so that we have only y's on one side of the equation and only x's on the other side of the equation. Because then what we're going to do is we're going to integrate with respect to y on one side and x on the other, and then solve for the equation. So this says our goal is to move all the y terms to one side and x terms to the other side. There is a disclaimer in that sometimes it's easier if we keep all the baggage, all the extra stuff with the x's than with the y's. Because my goal in the end is to find the function that satisfies the differential equation. And a function is y equals. So if I can get rid of all the stuff that goes with y and move it to the other side to start with, then when I go to integrate, it makes it a little bit simpler. Sometimes it's not possible. Sometimes it is. Now, we're going to integrate one side with respect to y, one side with respect to x. Now, we're going to put the constant of integration only with the x. I'm going to show you why we do that and why that's acceptable, but we don't want to have to write constants of integration over and over, so I'm going to show you why we only stick it with the x. And then we're going to simplify. Now, I am going to give you a caveat to this simplify, because simplify makes it sound like it's going to be some nice, pretty answer all the time. I wish. You know it's math. That's not probably going to happen. So simplify. Sometimes this means we want to get y alone. That's sometimes what simplify means. And sometimes what simplify means is other times it means keep it pretty. And I'll show you what that looks like. And pretty is a loose term, obviously. But to keep it pretty, because sometimes it doesn't make sense to get y by itself. The process to get y alone creates some unruly looking, fraction or square root, cube root, something like that that just gets real messy real quick. And so it's easier to keep it pretty in the pretty form. Here's the good news. Most of the time when you do this, it's going to be a multiple choice test. So you're going to know pretty quickly if your answer should look pretty or if it's a little bit messier. Typically solving for y, we can get a little bit messier. So, ready to try one? Yeah, great. Okay. Let's solve dy dx equals y squared. So think about what this graph might look like if you were to graph this. We only have y squareds if we were to look at slope fields. So horizontally, it would all be the same, right? Because we only have y terms. So the x, doesn't matter what x is, y is what's changing. All right. I'm going to walk you through this separation of variables in a slow, methodical way to start with, letting you know that most of the time I'm going to skip a fair number of steps. And most of the time you probably will as well, because otherwise it gets a little tedious. All right. So if it's not already in dy dx form, I tend to write it in dy dx form. Like for example, example 3 says y prime. The first thing I would probably do is rewrite that as dy dx, because we'll need to move the different terms apart. This one happens to be, so we're good. Really, I'm just rewriting the problem. Okay, I want all my x's on one side. I want my y's on the other. I can't move things by addition. Here's why. If I were to subtract y squared right now, I wouldn't have a way to get the x to the other side without it impacting the y squared, right? So we want to move things by multiplication and division most of the time. So I would multiply both sides by dx. Why? Because on the left-hand side, that would leave me with just dy. And on the right-hand side, that would leave me with y squared dx. Now here's the problem. We've got y's on both sides. My x is by itself, or on one side of the equation, because there's only one x term, not dx term, but my y's are not. So what I would do now is divide both sides by y squared. Now, probably when I write this, I'm going to write this so that it's easier for me to integrate. And maybe even write it so it's y to the negative 2 dy equals dx. Notice now that I have all my y's on one side, my y terms, and all my x's on the other. You see it? And now I'm going to integrate. I'm going to integrate each side with respect to the variable of that side. So on this left-hand side, I'm going to integrate with respect to y. On the right-hand side, I'm going to integrate with respect to x. So let's do it. Integrating with respect to y, we would go up degree times -1 or divide by -1. Okay, I am now going to write something, because you should write this when you integrate. I'm going to write a plus c. I'm going to call it c1, because this is my constant of integration. And what I want to show you in these next few steps is why we only keep it on the x normally. Okay? Now, if I integrate dx, what do I get? Okay, x plus, I'm going to call this constant of integration c2. Now, here is why we don't write constants of integration on both sides. My goal is to get what by itself again? Y. I want to figure out what y is. Well, in the way of y is that c1. So let's start with that. So the thing that I would do now is I would subtract c1 from both sides. In subtracting c1 from both sides, I'm taking c2 and I'm subtracting c1. What's the result?
C2 minus 1.
C2 minus c1, but c is a
Constant.
C2 is a constant, c1 is a, and what do I get as a result when I take a constant minus a constant? A constant.
C3.
So, in the formal math classes, you might see this labeled as C3. I'm just going to call it C. It's fine. If you watch videos online, you may see some people be real particular about it. And there is a time and a place for it. here is why I only put my constant of integration with the x terms. Because eventually my goal is to solve for y. And so I'm going to move that constant of integration that's attached to the y over anyway to create a new constant. So this is why we keep it. Does that make sense as to why we only add it to the x side? It becomes less relevant to the y. All right, my goal is to solve for y. So I'm going to multiply both terms by that -1. So we get y to the -1. I'm going to rewrite it as 1 over y equals -x. I'm going to call it plus c, even though I'm multiplying by a negative. Why? Why can I do that?
It's a negative number.
Right. Does it matter if c is positive or negative? Not really. It's a constant. It could be either positive or negative, and we'll get the same result when we take the derivative. Because the derivative of a constant is 0, regardless if it was positive or negative. So I'm going to let that c kind of absorb that negative. So we get 1 over y equals -x plus c. Or I want to know what y equals, so I've got y equals 1 over -x plus c. I have just solved for the function, or the family of functions, that solve the differential equation dy dx equals y squared. If I were to take the derivative of this expression and substitute it in place of dy dx in this equation, and then substitute y squared into the derivative of into the differential equation, we should get the same thing on both sides. That's the point. Yep.
Just to confirm, you could do -1 divided by x plus c and that'd be the same result?
You sure could.
Okay.
-1 over x plus c would be the exact same thing. Yep. Sure would. Questions on this? All right. I want you guys to try example 2. It's a little bit messier to start. And there's some algebra work that we're going to have to remind you of. Some properties of exponents, logs, our favorite. Definitely. All right, try it. All right, while you're working, I'm going to go ahead and separate this. So if you got lost somewhere in the mix, what is happening? My iPad is like done for the day. It keeps doing, yeah, you too? Me too. Really, I just want to put on sweatpants and a sweatshirt. I don't want to be, I'm not even that dressed up, and I don't want to be dressed up. I just want to be in sweatshirts, sweatpants, uncomfortable shoes. All right, most of the time, when I start these problems, I'm gonna separate it without much work. Take as much or little work as you can to separate it, or want. So I know I need to divide by y. I know I need to multiply by x, or dx rather. So I get 1 over y dy equals x dx. Great. Now I'm going to integrate this. And so we get the natural log of the absolute value of y equals x squared over 2 plus c. Good? Now, some of you might think this is pretty enough and we're good. And I don't, if I'm going to be honest, don't disagree with you that this does look prettier for now. But this type of setup is a very common differential equation, which has a lot of applications such as growth and decay and heating and cooling. And it usually, more work needs to be done. Okay? So let's do some algebraic manipulation of this. Remember, my goal is to get the function that makes this equation true. So ultimately, I'm trying to solve for y. So I need to, definitely unlog it. So the way I'm going to do that is I'm going to exponentiate it. So I am going to not do that. I'm going to do e raised to the power on both sides. And the advantage of doing it that way is then I can, because e raised to the natural log of anything is just that term. So we get the absolute value of y equals e to the x squared over 2 plus c all in the exponent. Okay?
And that's the something.
It's not our answer just yet.
You have to unabsolute it.
We got some more work to do. Okay, this is where remembering your exponent rules will come in handy.
Because the Ln is just log base E.
That is true. All right. I'm going to rewrite this. I'm going to do the opposite property of saying, hey, if your bases are the same, we add their exponents. Now I'm going to go backwards. The exponents are added, and I'm going to make them have the same base. Do you agree with that? Why would I do that? Well, perfect. E to the C is just a constant. It's just a number. So I'm going to write this as some constant times E raised to the x squared over 2. Now, truthfully, I need to do some more work because I've got the absolute value of y. I don't want the absolute value of y. Talk to me what absolute value means. What does it even mean? Say that again, TK. Distance from 0. Distance from 0. So if I'm 5 units from 0, do you know where I'm at? Well, I could be at positive 5, or I could be at negative 5. Right? That's reversed for you because I'm basic. But anyway, I could be at either of those places. So really, when we take the absolute value, if I want to remove the absolute value symbol, we get y equals plus or minus c e to the x squared over 2. Are you ready for a fun thing? We don't leave it plus or minus c because we have a constant. Does it matter if the constant is positive or negative if it's a constant? Not really, because it'll still be a constant. So typically, this will be rewritten, and oftentimes another variable is introduced. Whether it's called A, B, I'm okay if you leave it at C. Oh, that got real messy real quick. This is supposed to be an x squared over 2. Don't know what I wrote. And this would be my solution to my differential equation where c is a plus or minus of the other c, which is plus or minus of e to the c. This becomes a very common process that you're going to go through when we start talking about growth and decay and Newton's law of heating and cooling.
So when you're saying A or B, like
Sometimes, so you may
classic on it.
you may see this written as something like y equals a e to the x squared over 2, just to differentiate your constants. And again, watching the videos online, if you watch somebody, especially if you watch from like New Zealand, Australia, most of the Asian nations, they will be very specific about their constants and labeling their constants. And they're fun videos to watch because, one, they call it maths, regardless of what you're taking, and I love that.
There's multiple math.
Math. Yeah, do they just say we're doing maths? It's plural. And also, but they are particular about their constants. So if you see a different constant, that's why, or if you hear a different constant, that's why. Also, they say Z. I like Z.
They do say Z.
Z instead of Z, which makes sense. Think about all the letters that rhyme with Z. B, D, G, you know, like they all rhyme. So Z is very like different letter.
You're done.
Nothing rhymes with Z. No other letter rhymes with Z. Anyway, lots of them. I like that you went to bed. Come on. It is 7th hour.
It's good that you're not an English teacher.
Yeah. It's life. All right.
Literally the next problem in the test, just do any words rhyme with Z and just be like sometimes, always, or never.
Yeah, right. That'd be a fun question. No, I'm just kidding. All right. I want you to try example 3. Try example 3. This one is kind of ugly. It's not pretty.
Did I do something?
Let's look at this one. So the first thing I would do is rewrite. I probably would even rewrite this and move the 3e to the x over. Okay, and now I'm going to separate them. Now, we mentioned that you should take as little baggage as possible with the y. Yep. What I said, yes, to get, fair enough. I did say that. What I mean by don't move, use addition to move is I don't want to, like, let me back up. So for example, this is easier to explain. I can't move this to the other side by subtraction because then if I go to multiply by dx, it ends up with a dx attached to it. So I want to move by addition and subtraction only if it allows me to get an entire expression to one side so that when I multiply or divide, that it's not impacting, like it doesn't change. I don't have a y attached to an x. Does that make sense? Fair enough. I can see why you... I also did say at the beginning that we don't want to take very much baggage. So you could divide by the 4 if you wanted. You're going to end up multiplying by 2 anyway. You're going to end up with a constant on that left-hand side regardless with the y. So you could leave it if you want. You can move it if you want. That baggage is not as important to me. So let's integrate. I would go up a degree, divide by that degree, which would make this 2. Y squared equals favorite integral ever, plus c. Okay, now, not fantastic at this point if we're trying to solve for y, although we're going to come back to this because it is possible this is one of your answers. Are you okay if I leave this as, when I divide by 2, 3/2 e to the x plus c? Do you think I need to do c divided by 2? No, because c divided by 2, constant divided by 2 is still a constant. Again, you could label it differently if you wanted. Now, if I take the square root here, when we take the square root of a number, the answer that we get is plus or minus that square root. Plus or minus in this situation is important. It cannot be absorbed by that plus c, nor can we pull that plus c out because it is underneath the radical, and I would need to deal with the 3/2 e to the x plus the c before taking the square root. Now the plus and minus will come into play on this next example when we have an initial value and we have to determine whether it's supposed to be positive or negative based on that. But this is an answer. Now, did any of you like any other answers better? It is very possible, very possible that the answer you see is 2y squared minus 3e to the x equals c. The reason why is we have a whole type of differential equation that we solve if the function is equal to c. And so sometimes if we can get it so that it equals a constant, the function equals a constant, that is all we need. So, and it's prettier. There's less mess on that one. You'll know, you guys, it's multiple choice. So is your answer pretty in the multiple choice or is it not pretty? Do you need to keep going and simplify more or do you not need to keep going and simplify more? On FRQ, they would take either. Good so far? Great. We're going to look at one more classification of problem. And that's like example 4, example 5. We're only going to do one of them. We're going to do example 4. But this type of problem right here, where we have not just a differential equation, but some condition, some stipulation about this problem, this is called an initial value problem. You will see it abbreviated as an IVP, or you will hear people talk about initial value problem. This is an initial value problem. So, what we're going to do is we're going to find a solution that satisfies this initial value problem, which means we're not going to have a plus c in our problem anymore. We're going to solve it and get something that no longer has a plus c. So here's what I'd like you to do. I would like you to separate and try to integrate and stop there. Separate and try to integrate and then stop there. Here we go. So, how many of you got stuck?
Half the test is
Yes.
half the test is bubbling.
Okay. Did we get this far? Okay. Woo! Then we need to integrate. And this left-hand side, you probably did just fine to get y squared over 2. It's the right-hand side.
Separate it.
Exactly right. U substitution's not going to work. Integration by parts might work, but be a pain. Actually, I don't think integration by parts would work well at this. But I can separate that fraction. X, if I put x underneath each of them, 1 over x plus x over x, I get 1 over x plus 1 dx. So we get y squared over 2 equals the natural log of the absolute value of x plus c. Here is where I would use my initial value. I wouldn't get y by itself first. It's not wrong to get y by itself first. There's nothing that says you can't do it that way. What I have found is that to me it's easier to plug in my initial condition first and deal with it and get it as simplified as it can be at that point, and then go to try to get y by itself, because sometimes when we get y by itself it creates this really complicated problem, and then plugging in an initial condition makes it even messier. So we would get negative 4 squared over 2 equals the natural log of 1 plus c, which gives me 8 equals 0 plus 1 plus c, so c equals 7. So we get this equation that's y squared over 2 equals the natural log of the absolute value of x plus 7. Okay, I'm going to multiply everything by 2, so we get y squared equals 2 natural log of the absolute value of x plus 2x plus 14. And then to get this solution, we would take the square root, which would be plus or minus the square root of, you ready for some log properties? No.
Still writing.
I'm going to take the plus or the minus the square root of the natural log of x squared. The absolute value can go away because I'm squaring it. It will always be positive. Yep.
You can finish first.
Well, I'm done with what I was about saying.
Okay.
With that.
Okay, so when you, let's say you when you're solving for c, you simplify y first. Can you just keep it c, or do you have to do if you multiply 2 over, does it have to be 2c when you solve for c? Because I got
So-
14 one way and 7 one way.
Well, you lost. So if you multiplied by 2, you'd have to do it to everything. So this would be 2 times the natural log 1.
Right.
This would be 2. This would be 2c.
So I can't hide the c. 2
You
minutes.
cannot hide the c at that point.
I have to carry over the.
Yes, I see what you're asking. Good question. We can't just absorb it at that point.
Okay.
Because then it would really be 2c.
So we can
Yeah.
write anything that's oh, it was,
Yeah.
it was absorbed by the sea.
Yes, go ahead.
How do we get the x squared for the natural log again?
Because the rules of exponents say that if it's a coefficient, it gets moved up.
Oh, okay, that makes sense. Would it be
Jasper?
fine
If you write natural log, this is parentheses, would you put a square inside or outside?
I would put it inside. Now, this answer's not done. It's not actually correct yet. Here's why. I have plus or minus. I only want the negative. Any guesses as to why?
Oh,
Negative 4.
Because this is negative 4, my plus or minus would match whatever the sign. So if this had been y of 1 equals 5, I would take the positive square root. But because it's negative 4, I want the negative root. Now, 2 types of problems we have here that that I'd like to talk about. One, and then I'm done. This right here with the plus c, I didn't really solve this, but with a plus c, this is called a general solution. General solution. Whereas if we plug in an initial condition, the result that we get is called a particular solution. What is happening to my iPad?
You need a new tab to your phone.
I could, actually. I've wondered when I need to replace it. I've not done it. So this is called a particular solution. So if we plug in initial value, we found a particular solution. Kind of like on the graph. When we were able to sketch one curve, it's because we went through a particular solution. Otherwise known as general solution. Good? Questions? Math lab tonight. And last night, for those of you that didn't log in.
I did.
Oh!
It's the first day back. We have that much work. Like we can do it.